Do you guys remember how in the last, it wasn't the last chapter, but in chapter 8, where we talked about alkene reactions, we kind of in an awkward way introduced this one Anti-Markovnikov reaction that involved the addition of HBr, hydrobromic acid, across a double bond, but in an anti-Markovnikov regiochemistry, meaning the bromide, what we typically think of as a nucleophile, ended up on the less substituted carbon, so that when we compare the regiochemistry, it kind of looked like this, right? This would be racemic because to the carbocation, bromide can add from either face, and that would be the Markovnikov product. But HBr with some sort of an alkyl peroxide gives you the anti-Markovnikov addition of HBr. So this would be Markovnikov. And the latter would be anti-Markovnikov, right? The one thing we didn't talk about back then in chapter 8 is that is the mechanism. So here we want to show you the mechanism here. The study material, of course, is the alkyl peroxide. This thing, same thing, right? There'll be a diethyl peroxide, okay? And what happens is that this needs to be initiated. So typically that involves either heat, or some sort of UV light, or it could even be like regular light is enough to get this going. So that's why I'm not necessarily showing you the UV light symbol or anything like that in the reaction equation up top. But the first thing that would happen is homolytic cleavage of this very notoriously weak oxygen-oxygen single bond, which will give us this oxygen radical. And just to be thorough about all the electrons around the oxygen, that's what it would look like. Typically, this would be just drawn as that. I want you to know. But that's I guess we get two of these, right? But this, again, just like with the halogen molecule being homolytically cleaved, this is a very rare event, meaning this is just something that happens just to like one of many molecules in the mixture. Also, this peroxide, we would be adding only a catalytic amount. Maybe that's worth noting here. It's not, you're not going to need a stoichiometric amount of this. And the reason is that once you get this one radical, right, what can happen is this could react with HBr like so. And so the hydrogen bromide will end up becoming a bromine radical. Maybe and you get a non-radical stable ethanol molecule back. Here's a bromine radical. And now this could propagate further by reacting with the double bond. Now, this is going to be another propagation step right here. But we haven't seen how propagation might work with double bonds yet as far as the mechanism goes. And here's another type of propagation. It doesn't necessarily always have to involve abstraction of hydrogen radical or hydrogen atom. What can happen is radical can add to a double bond like this. So this pi bond, right? Remember, it's made of 2 electrons, so I need to have 2 half-headed arrows to show what happens to those 2 pi electrons. And then once that happens, we get that radical species. Now the alternative would have been this mechanism, where the bromine adds to the more substituted of the two carbons of the olefin, or the alkene, and in that case we would have had this radical. But you guys might recall that because radicals are electron deficient species, the more substituted the radical atom is, the more stable it is, right? So between the two, this right here would be the more stable of the radical, and so for that reason this is what gets produced more. Right, so we're going to continue with the mechanism with this radical here, and remember this is once again a propagation step. Okay, and this is not the product yet, what we have here. So the next step, again, our final step also needs to be a propagation step, where one of the products has to be a radical for this to become a chain reaction that keeps going to produce the product in good yield. So that's what's going to happen here as well. That's just known to be so by experiments. I'm going to draw the hydrobromic acid kind of backwards, because what can happen with this radical is that can abstract a hydrogen atom. And then you might think, well, why doesn't it abstract the bromine of hydrobromic acid? That's a great question. The reason is, if you were to abstract the bromine from this, what gets left behind is a hydrogen radical, which is not as stable as bromine radical. As you can imagine, bromine radical, it is still a very reactive, unstable radical, but because it has so many electrons, bromine doesn't mind being one electron deficient as much as hydrogen would. Hydrogen is the smallest atom, and therefore to be a free radical, that's a very unlikely scenario. And that's why this is going to abstract hydrogen atom instead of the bromine atom from hydrobromic acid. And the result of that, of course, will be is that we get the product. This is a product with the hydrogen right here, which I'm not going to draw just for simplicity's sake, but it is a propagation step, because we get a bromine radical on the side, which can continue the reaction further, right? So this is still a propagation step, and this can continue to react. Right, remember the bromine radical is what adds to the double bond like so. Okay, so this is a type of an addition reaction that we didn't cover in chapter 8, but now you know. So maybe hit the pause button here real quick to see if you can predict the product of this reaction right here. All right, so if you worked on this, hopefully you could tell that the product is going to be like so. Now here I'm purposefully being vague about the stereochemistry. You could kind of, to be more strictly correct, you could show how both of these would be ambiguous mixture of stereoisomers at both of these chiral centers. So you could draw it like that, but when you have a multiple centers that are ambiguous, it's okay to draw it like this. Okay, so that would be the product, but I want you to notice the anti-Markovnikov regiochemistry here. Okay, now coming to the very last reaction that we want to learn this semester, which is still really the same reaction as what we just did here, anti-Markovnikov addition of a radical across a double bond. And what we want to discuss here is the application in the industry, and that is polymer or plastic synthesis. You guys may have heard about like polyethylene plastic that typically has the PE abbreviations written on the plastic product. The way that's synthesized is by using ethylene, or ethene is the more IUPAC friendly name, but a bunch of ethylene gas at really high pressure. That's 1,000 times the pressure of the regular atmospheric pressure, and at high heat. If you give it some small amount of radical initiator, maybe we'll write that here. This is again, this is just used in a catalytic amount. You only need just a little bit. You can produce a polymerized version of this, and the mechanism is radical addition to the pi bond. And often the polymer structures are drawn like this, with the N being like a really large number. A typical polyethylene molecules would have like thousands of monomers. So that's another terminology that you may or may not have known before. This would be our monomer, and this would be the polymer, in this case PE, or polyethylene glycol. I mean polyethylene. Okay. Polyethylene glycol is what's used in mRNA vaccines and such. Similarly produced, but structures different. That's for another day's discussion. But here's the structure of polyethylene, and then of course it's so large that we're not going to draw the whole structure, and that's why we put the repeating unit in the parentheses right there. Okay, so that's typically how we draw the polymer structure. But basically, I just want you to notice this is a really, really long alkane chain. Like it just goes on and on. Right. That's what polyethylene is. But here, what we're interested in is the mechanism. Here's our notoriously weak oxygen-oxygen single bond at high heat. As you can imagine, that's enough stimulation for this bond to be homolytically broken. And once that happens, of course, we're going to have a free radical that can then add to the double bond or pi bond, right? Remember, those are very easily accessible to electrophiles, and radicals are kind of a electrophile. They can add like so. And this is still considered a propagation step. I want you to notice that, because you would still end up with a radical there. And now what happens is that radical can, instead of reacting with something else, can react with another molecule of its own kind, another monomer or another ethylene molecule. Like so. That would leave radical on the second unit, right? And then of course this can react with another molecule of ethylene, and that's how the chain will continue to get elongated over and over again. Okay, and at some point this can this reaction can run out of steam, and the terminal radical can experience some sort of a termination step where like two radical chains react with each other, or it abstracts something like hydrogen from something else or what have you. It's not always clear the exact termination reaction that happens, but when that happens, you of course get your polymer product. Okay, so that I just want you to be aware of the reaction mechanism here, which is really similar or basically the same as what we saw with the addition of HBr radically across a double bond. Okay, now here, this would be a good time to pause your video to answer the last question here. What kind of a molecule would you get from this last example shown? Now, as you might be working on that and reaching for the pause button, I might want to mention that one branch of organic chemistry that I typically don't end up emphasizing very much is polymer chemistry or polymer science, which is a very active material science field that's very much needed in the society. Being able to come up with new types of plastic material that we can synthesize, or maybe coming up with a more efficient method, chemical engineering method of producing plastic and what have you. It has a lot to do with how to do these polymerization reaction under radical condition. That's a field of study in chemical engineering and polymer science that people look at a lot, and this is just kind of a taste of that. But partly because my background is in medicinal chemistry and pharmaceutical sciences, that's not a field I tend to emphasize on in the class, but I just want you to have some exposure to this field. So let's think about this reaction right here. First, I might want to let you know that this monomer is called styrene. This vinyl group coming off of benzene is called styrene. And the typical initiator that people use, because up here we didn't really specify what the R group is of the initiator, the typical initiator that's used in polyethylene synthesis, and you might be able to guess now polystyrene synthesis, is butanoyl peroxide, which looks like this. Of course, the mechanism of the initiation will look like that. But with that initiator, what happens is this alkene will be polymerized, and this is going to be the repeating unit. So instead of having just ethylene like this being the repeating unit, the second carbon will have a phenyl group being part of the repeating unit, and this would be a polystyrene. And the mechanism is basically the same. I might point out that the key intermediate will be like so, where the radical is next to the phenyl group, because there's actually resonance stabilization of that, and that's what adds to the next styrene molecule, and then the next, and so forth. Okay, so this is if you're not familiar, polystyrene is just a chemical name for the material that makes up styrofoam, which is a proprietary brand name. But anyway, that is it for chapter 10, and that is pretty much it as far as new materials for the semester. Good job for getting through the whole semester of organic chemistry.